Circuit below shows a... Yeah, you need me to go back?
Yes.
To which? The diagram?
No, the final one.
Oh, the drive. Yeah.
No, not the right.
This? Oh, this part?
Yeah.
Yeah. No problem. Okay. So in this circuit here, this is actually like a battery here. Do you remember? This is the pure voltage, so to speak, and this is the internal resistance. There's an external resistance and there's a voltmeter here. And basically the question is, prove this formula. So I'll draw this and then we'll try to prove this formula. So let's do our best. Because I know proving is difficult. So we have this one here. And then we have this small resistor here. And then we have this big resistor here. And then we can measure the voltage here. Now, we can use Ohm's law, we can use Kirchhoff's rules. So what we're looking for, if we go back to the question, is he wants a formula for the small r. So let's see what we can say. If we use Kirchhoff's, we can go, well, I mean, this is the only circuit here, okay? This isn't even part of it. This is just to measure the voltage. So we can say this minus this one. So that would be I hope this doesn't confuse you. Maybe I should write it out a bit clearer. So, yeah, sorry, I'll start again. I'm using the loop rule.
So we're going left.
And I'm going left, and there's no junction here, so I can't use the junction rule. So I use the loop rule. So the loop rule says I start with this, and then what happens when I get to this resistor? I lose voltage, so it's minus V. Okay? This, because the voltage we know from the machine is V.
Okay.
So that V is the reading on the machine here. And then we lose a little bit of voltage here. But the amount of voltage we lose here, we have to use Ohm's law. So the small voltage that's lost here will be equal to I times the small r. Does that make sense? This is Ohm's law.
So we're going around the outer...
Well, there is only one loop, because this isn't really part of the circuit. This is just to measure the voltage.
Okay.
So it's not really part of it. So that should equal 0. Okay. And this one here, that one there, that came from Ohm's law. That the voltage in the small resistor should equal I times R. Yes, is that okay? So if I rewrite this, I can get that minus that over that one there. That's equal to the small r. Now I don't quite think that's what he wants. E minus V over V times r. E minus, okay, so what we have to do is something with this I here. But you know, again, if you use Ohm's law on this one, you have big V equals I times big R on this one here. So the I here, you can write it as big V over big R. And that's the answer. That's what they ask you to show.
Why big R?
Because that's what they wanted. They wanted the answer like this. So what I said at the end was, this I here, I can get it by using Ohm's law on the big resistor.
Yeah.
Big V equals big I by big R.
Okay.
Are you okay?
Yeah, just for me, through my pen and she didn't give me that.
Who didn't give you your pen back?
So,
Fumi. Can't turn your back on
maybe
Fumi.
she forgot.
I thought it was something more serious.
Well, she
It is serious, Brendan.
rewind the corrector.
Oh, corrector pen, alright. Yeah, this isn't just a cheap pen, Brendan. This is the corrector pen. Alright.
Wait, like, whiteout?
Yes, the whiteout. Now you understand?
Yes.
Okay. And that's part A done. That's nice. Okay. Part B. Two lamps A and B are designed to operate on 240 volts AC. The lamps are rated at 60 and 40. They are connected in series to 240. Give a labeled circuit diagram of this arrangement. So it's 60 and 40 and a 240. Okay. .240 volts, 60 and 40.
Are those resistors?
They're lamps,
Oh, okay.
which are effectively resistors. Now, I don't know if I told you this. You have to tell me if I told you this. Did I tell you the difference between AC and DC?
No, but
Yes. No, I don't know.
you didn't actually go through.
No, I don't think I actually. I don't think I ever explicitly said the difference between AC and DC. Sayun, do you know the difference between AC and DC? No, because I don't think I ever said it. Oh, you never heard of it? Okay. If you look here,
It's a bag.
no, I knew. I was waiting for you to say that. You see these here? These are AC, and then with a small battery, that's DC. And the difference is just this. I'll go to the side here. DC, AC, time, current, time, and current. So for a battery, it just looks like this. Just constant current. Yeah? Doesn't change. But for AC, it goes like this. Huh? Now, let me explain what's happening. It's like the charge, the Coulomb. It goes forward and then stops and comes back. That it keeps changing its direction. So it's like if I have a battery and then I do this and then turn it around, I keep doing this. So for all of our circuits, we must use this. Because if you think about it, if you have a capacitor, okay, if the charge goes in this way, and then if it then comes back, then it could cancel the charge built up inside. You know what I mean? So everything we've done so far has been this. Everything. AC is like, okay, it's like 99% this and 1% of this. So the only thing you really need to know about AC, it's like DC, except it just keeps going back and forth, back and forth, back and
I
forth.
thought AC was far more effective in terms of like it's what's used for transferring energy.
It is. But this is maybe more, that's more history class than physics class. It's to come with, it came down to, this was for Tesla, no, make sure I get these the right way around. Tesla Edison. No, the other way around, sorry. No, this was Thomas Edison,
Yeah.
and this was Tesla. Thomas Edison won out because it's cheaper to use alternating. Tesla wanted to use direct.
No, it was Tesla who wanted to. It was DC that started out with Thomas Edison, and then Tesla discovered DC.
I'm not 100% confident, but I am pretty confident though it is the other way around, because I do remember Thomas Edison always wanted to use. Oh no! Now that you've confused me, now I think it's the other way around.
Thomas Edison
just give me a few seconds.
Okay. I remember watching a YouTube video that went through the history of this and how like Thomas Edison was such a meanie. Even though
You know what? I'm too confused now which way around it is. Sayur, do you know the person Thomas Edison? Do you know this name, Thomas Edison?
Yes.
I know Thomas Edison. And do you know the guy Tesla? Yeah. This is around about 1900.
he was the Edgar Allan Poe of physics.
One of them wanted to use AC and one of them wanted to use DC. We think Thomas Edison was AC or DC?
I still think I know that Thomas Edison is DC, but you think it's the other way around.
I don't know.
I think
You know what?
research here.
This is exactly what Wikipedia exists for. Anyways, which one do we use in our homes? We use AC in our homes. The reason AC is used is because it's cheaper, basically. Do you want to look it up?
How is it that
DC,
like if we were to use DC with power plants and the like, I know that the power lines would have to be super massive.
yeah, DC versus AC, you see.
It's Korean.
That's okay, once you can read it. Anyways, the problem is with DC for power DC, it's terrible for long range,
Yeah.
but fantastic for short range, and vice versa.
But why is it that with AC the temperatures within the coils they remain the same, whereas with DC they overheat, and that would cause melting.
You know, it's not really in the physics book, but I do wonder if we try to draw an analogy, like in the DC case the current is constantly going in one direction, whereas in the AC case the current is going back and forth. So I do wonder if the back and forth offers some kind of almost like a relaxation, I'm not sure actually, I have to look it up. But AC is good for long range, bad for short range. DC is good for short range, bad for long range. Did you get that page? I mean, like it's in English now. Yeah, either AC or DC. Yeah, so DC just means it moves in one direction. AC means it keeps changing directions, back, forwards, back, forwards, back, forwards. That's all.
So AC is good for long direction.
Yeah, AC is good for long distance. DC is good for short distance. So all these here in the house are all AC. But then you see this here DC. Yeah, this DC, but then they're AC. Okay, anyways, continuing on. So,
Why is this gun so ugly?
it's his fault. Right, give a labeled circuit diagram. So, we have to fill out this table, okay?
This one.
So, firstly, 60 and 40. Okay? So, we want the resistance in each. So, if we go back here, okay. Where's my diagram gone? Back to over here. Okay. So, we want the resistance in each. So, what formula could we use? Yeah, well, let's look at all the formulas here. We have, do we know the I? No, we only know the V and the P.
Yes.
So,
So
P equals IV? No, we want the or in it, sorry. So, P equals I squared or, so we could have P over I squared? No. P equals IV? Maybe we should write them down.
Yeah, we need the V.
The first one we want is the resistance, and we have the P, and we have the V.
But we need I so that we can use the
But
I and the V to find
what's strange is I want to do it in the order that they ask, and the I is the second thing. You know what I mean?
Notice.
There, hang on, let's have a look at the formulas again. This one, no. Which one do you think? Yeah, the only problem is we don't know the I. And yeah, maybe you could use this. Yeah. See, the only reason I'm worried about this is because if you look here, they ask for the I second. You know what I mean? So anyways, I'm just going to check the answers. Be the easiest thing. Worksheets. Physics. No. Yes. No. NCUK. Past papers. Physics. Let's say around about maybe here. Any ideas, Kirby? Let's see. No. Okay, maybe it's it's marking scheme.
Wait, would we add the power sources together or separate them?
That's the other, I just want to have a look at what they do here. What's the first? I'm looking for it. No, okay. It might not even be this here. I'm looking for a little table. No. All right. That was that one. So let's try 0708. All right. So it is version 1. I go too far. Yeah, I think that's what you were saying, Sayun. V power equals V squared over R. So resistance equals. Yeah, they use power as V squared over R, but you notice that.
Is that 900 or 960?
Well, I'll write it down now. I don't think that's in the formula book. So this is one of these formulas you have to make up yourself. So what I mean by that is you have power equals I squared R, but you don't know the I, but you have Ohm's law, V equals I R, so I is V over R, so you get V squared over R squared, R. So that's V squared over R. Yeah? Okay, and so we get R is equal to V squared over P.
And you should get 960 ohms and I think 1000 kilo.
So yeah, we'd get 960 and 1440, is that the other one? So when you put in the V and the P.
Yeah, 1440.
Okay. 1440 ohms and then 960 ohms.
Yeah, we could have used P equals IV and then
It just
individually it would have been the same.
it felt bad. It felt wrong.
Okay.
This is for R.
Yeah. We have to use this formula. We have to put together. We put Ohm's law formula into the power formula to make this new one here.
But this is the second time that it's worked effectively.
I know, but you know, there is something to be said about listening to your instincts.
Okay.
You know.
No, I just want to figure out why this would be less trustworthy than that.
It's just feelings.
Okay.
It's just feelings. All right. Next part we need is the I. So we can say the I should be the same for both, shouldn't it? Because
No, I got different values.
oh, this is concerning.
That was how I was able to determine value of R, seeing as V remained constant.
Oh, okay. I don't know, Brandon, it is the same. 0.1, 0.1.
So how do you figure that out then?
Well, remember, if 1 coulomb goes in, 1 coulomb comes out, so the I should be the same for both.
Yeah, technically, but there's
Technically.
some-
Yeah, okay, no, I
Sure.
get what you're saying, yeah.
Yeah.
Alright, so how to find the I? Oh, I get what you're saying, because you say V equals I or, then you get something different.
Yeah.
But what about if we use this formula here? Then we could get I is equal to square root P over R. So that would be square root 60 over 960. So what's that? 60 divided by 960 square root. That's, well, that doesn't match up at the back, 0.25.
Yeah, that's
Is that what you got?
what I got for the 60 and 1 over 6 for the 40.
Scratch head. That's okay.
What is
Huh? Well, it should be the same, but the question is why or how to calculate it. Because should we use maybe one of Kirchhoff's rules? I think Kirchhoff's just for decent. Let me see what they did. Oh, yeah. Oh, that's stupid. I feel dumb. Okay, so what you do is you just put them together as one large resistor.
Okay, so
Yeah. Yeah. So if you put them together, you get 240, and then you get 100, and the current will be from just V equals I or. So 240, or you also have P equals I squared or.
Yeah, that's 0.1.
Got 0.1? Oh, I added it's not 100 here. What's the total resistance?
Total resistance is 2,000.
No, it's not. That's the resistance. 960.
That's for 1,
Yeah, plus 1440.
which is
2,400. Yeah. So then that means the I has to be 0.1. Okay. And the I here, it has to be the same throughout, because a coulomb in means a coulomb out.
So these weird things just what exactly would that mean? I mean, using the method that I used, I found that the current for the 60 watt lamp.
But the thing is, you see, what voltage did you use?
Same voltage.
But it's not the same for each.
Okay, that's
the problem, yeah. Because the first one will drop the voltage by the time it gets to the second one, yeah. Right, sorry about that. Is that clear how I got the I as this? That's all for the I. And it's the same for both?
Yeah.
Okay. So 0.1. Now the voltage for each. So we can say V equals I or. We know the I's and we know the ors. So V equals 0.1. Now what's the first resistor? How big is it?
960.
No, resistance. 960?
Yeah.
So it should just be 96, and then the second one would be 144 volts. And you know what's nice? You know what's really nice? If you add them together, what will the total be? 240. Isn't that awesome? Yes. And if we look at the answer, there we go. 96 and 144. Yes? Right, the last one now is the power. Now this is where you have to be, I suppose, a bit careful. This is a 60 watt lamp and this is a 40 watt lamp. but that's just what's printed on them. Like for example, this one here, if you look up, this here, hey, look up Brendan, this is maybe 100 watts, and maybe this one is 200 watts. If I connect this to a battery, will 100 and 200 come out? No, the battery's too small. So this 60 and 40, that's just what is printed on them. But what will the actual power of the light be that comes out? It won't be 60 or 40.
It'll be an average.
Maybe it's an average, maybe they're both the same. Do we have a formula to calculate the power? Well, look, remember I said the previous part should help you. So here we have R, I, and V. So do we have a formula to get the P if we know R, I, and V? Yeah, maybe that's one. That's the one they go with. Power equals VI. So if we just multiply now. So 0.1 times 96, that will equal 9.6. And then the second one is 0.1 times 144, which will equal 14.4. Let's check if that's right. Yeah, there we go. Now, I want you to look at how strange this is. The second one is, which lamp will be brighter? So which one has more light coming out of it?
40.
Yeah, isn't that funny? The 40 watt light bulb has more light coming out of it than the 60 watt light bulb, see? So lamp B is brighter, even though it's a weaker lamp, because if you connect them together the way you did. Yes? Silence is good, or silence is we're tired?
It's just the sum of the voltages for each of the
Yeah.
lamps, it sums up to 24 watts, which is 0.1 times 240, so
These two,
it fits as well. Yeah.
it fits as well.
Yeah.
So isn't that kind of satisfying? Yes. Oh yeah.